Hey everyone, today we will be implementing the Dueling DeepQ learning algorithm. Like our previous double DeepQ learning video, there's about 99% of the code exactly the same as double DeepQ and the standard DeepQ learning videos, so just go ahead and take a look at those first. If you are uncomfortable with things like the replay buffer, sampling, training script, all of that stuff, I've implemented that all in detail in that DeepQ learning video. So just go watch that first, and then you can come back here and this will make a little bit more sense. But let's just do a super quick recap of the stuff that we've seen. So DeepQ learning was awesome, but there was a couple of issues. The first issue was that moving target problem, right? Moving target was essentially, if we're using one model to identify what is my Q value for my current state action and then my Q value for the next state action, then my TD target that I'm computing will continue to move, right? So as I update my Q model here, my main model, my Q values will continue to change, and the TD target that I'm trying to map to, right? That's what I'm trying to learn, right? I'm trying to minimize the mean squared error between my Q values and my TD targets. If my TD targets keep moving around, then it's really hard to minimize this mean squared error. So we dealt with the moving target problem by just doing this, right? We essentially created a Q target model that's not trained. It's just a copy of the Q model, and we periodically update it. And we've seen all of this earlier. And this brings some stability into our training because we can basically hold our Q target model constant for just a couple of iterations, right? Just keep it constant and give our Q model some opportunity to minimize that mean squared error. Then after a couple of iterations, we can then go ahead and update the Q target with the weights from our Q model and then just repeat that over and over again. And basically the idea is when we're computing mean squared error, we have basically a standard baseline, some baseline to minimize that distance to. So that was our solution here. Now, of course, the method from the double DeepQ learning algorithm, like we saw earlier, what we saw in the earlier video, was to decouple the action selection evaluation. The main idea was that when we are selecting an action here, so we're using essentially our Q target, we go ahead and pass our next states into the Q target, we get our actions, and we take the max right here. We take the max over what the Q target thinks, what the Q target thinks that next state should be. The problem is we know that the Q target is just a lagged copy of the Q model, which means the Q target model technically can't be as good as the Q model because the Q target is it's lagged, right? It hasn't had as much experience. So the decoupling that we looked at in the double DeepQ learning video was essentially this. Let's just go ahead when we want to identify for the next states, right? For the next states, what is my Q value, right? The Q value for the next state action pair. All we do is pass the next states into our actual Q model, the thing that's being updated, right? The most up-to-date model, and use that to identify what action should I take, right? What's the max Q value? Because I know this model here is better, so I can use that here. But I can't actually use this Q value because that would lead to that same moving target problem from earlier. So what we do is we say, okay, so this is the Q value that this is the action essentially that my Q model says that I should take. That's the best action I take. So then I can then go ahead and then I can index my Q target's Q value for that exact same index, right? So that's the main idea. Go ahead and just take a look at those earlier videos if you want some more details, right? But we have a little bit of an issue here. Not all states are equally valuable. So just to give a metaphor, here's the way I like to think about it. Let's say I'm taking two different classes. I have math and history. So those are the states that I have. And there's three different ways that I can actually study for these classes: YouTube, flashcards, and a textbook. Now, when it comes to math, I'm already pretty good at it, right? When it comes to studying math, it doesn't really matter what method I pick. I could pick YouTube, I could pick flashcards, I could pick textbook, but no matter what action I select to study for math, I end up always doing good, right? So it doesn't matter. And this is where you can start to see there's a little bit of a difference. Now, history, I'm really bad at it, right? I'm not as good. I cannot memorize things with flashcards, and I get really bored when I read textbooks. But when I listen to history lectures or podcasts on YouTube, I am very engaged. So the best way for me to study history is by watching YouTube videos. And so this kind of shows you exactly what's going on. In math, when I'm studying for math, when I'm in this state for math, it doesn't really matter what action I'm taking. But when I'm studying for history, the action matters quite a bit, right? Which action I select matters quite a bit in terms of determining how well I will do on my history exam. And this is why not all states are equally valuable. There's some difference between what state I'm in. And all the methods we've looked at so far doesn't really do anything about that. We just compute Q values for all different states. And that's it. We don't really think about it other than that. So let's do a little bit of a recap, right? The Bellman equation. So we saw this in our very, very early videos, right? But the Bellman equation was essentially this, right? It's everything we've looked at so far, but it's basically a couple of averages. We're essentially taking an average over the action of the sum over the next states and rewards. And we have basically the reward we got plus discounted future values. And we're weighting in by the probability of actually making that transition. Fine. But there's actually two different types of values. We have state values and then action values. State values is the value function that we're seeing right here, right? That's our Bellman equation. What is the value of this state? But this stuff on the inside is actually just our Q values, right? The Q value is the value of selecting some state and getting the reward for taking that action at that state, and there you go. So this internal part here is just our Q values. And if any of this seems confusing to you, just go watch my kind of in-depth video on the Bellman equation where we tear all of this apart. So the values are actually just an average of your Q values, right? So if you want the value of a state, all you need to do is just average up all of the Q values for all the actions at that particular state. So it's an average over the action space, and they're weighted by the probability, right, of those different actions at that state. So that's the main takeaway, TLDR. The values are just an average over the actions of the Q values, which are state action pairs, right? It's basically, the values are a marginal of your Q values. So the advantage function is extremely important because it's going to show up over and over and over again. It's going to show up when we do LLMs later. It's going to be all over the place. So the advantage function is extremely important, but also very simple. The idea is this. The Q value is a representation of what's the value of this specific state at this action. And the value is my average value over all those actions. So if I subtracted one from the other, well, that's just saying, what is the benefit of taking this specific action, right? This specific action over the average action, right? Over the average action. And that's the main thing. So you can imagine that you have all of these different actions you can take at a specific state, and you just average them up. And then you can see, if I take this specific action at this specific state, how much better is that than just taking the average, right? Whatever would have there been on average. And just going back to this example here, right? On average, all of these things in math kind of just are fine, right? I do well in math no matter what method I use, which means if I do well no matter what, then there's not really much of an advantage of taking one action over another. On the other hand, here, for all the different actions I can take, yeah, picking this good action here will be much better than the average. Because if I take the average of all of these, whatever the Q values for these would be, then of course it would be less than just this value here, because these are, let's pretend these are like negative Q values or whatever, right? Okay, so that's the main idea. The advantage function just tells me what is the benefit of taking this action over or instead of the average action, essentially, right? And that's my advantage function. Now, our neural nets, right? The end goal of our neural networks is to predict Q values, right? We want our neural network to predict the Q values. That's all we actually care about. So we can reformulate it. Let's just rewrite our Q values as the sum of the advantage of a state action pair plus the values of that state, right? Just rewrite it, no problem. And this means our neural network will look kind of like this. We pass in some states, and now our neural network has two jobs. Instead of, from before, where the neural network's goal is just to predict the Q values, we can just ask the neural network to do two different things, essentially disentangle those two representations. I want you to pick or learn for this specific state, what is the advantage of the different states, right? So what are the advantages of taking this action versus this action versus this action versus this action, so the four different actions at this specific state. And then I also want you to estimate what's the overall value of the state, right? The aggregated information, like basically the average over those. And with that, I can then add my value, that predicted value, to my advantages, and I get my Q values, because that's exactly what it is, right? My Q values are just those advantages plus those values. So we can just have a neural network, predict the values, predict the advantages, add them together, and get this. And that's it. That basically we've disentangled this representation. Now, there is a little bit of a problem with what I just said, and that is there is no identifiability. Now what this means is essentially if I have Q is A plus V, what happens if I shift V by some constant C? So I'm going to call V hat is just the original V plus some constant C. And then I'm going to take A and I'm going to subtract that same constant C from it. That'll be my A hat. Then Q is equal to A hat plus V hat. And this is a little bit of a problem. We can see we have completely different actions and values, right? So this action and value, and then my A hat and V hat, which is just a shifted version, they both will give me the same Q. Because if I do value hat plus action hat, that's going to be value plus C plus action minus C. The C's will cancel, and I'm just left with value plus action, which is again Q. So this is the non-identifiability issue of what we just talked about. There are multiple ways of getting the same Q values from a action and value, or from our advantages and values. And just to kind of ground this, right, we can start with an example here. Let's say we had the value of 5. The advantage was predicted as 2 of going up. Let's say there's only 2 actions, right? So the actions are up and down. So the advantage of going up is 2. The advantage of going down is -2. And so my Q up and Q down is just going to be the value plus the advantages. So it'll be 5 plus 2, 7. And it'll be 5 minus 2, 3. But let's say I shift everything over. So I'm going to shift my values by 5, so my 5 becomes 10, and I'm going to shift my advantages down by the same constant. So my 2 becomes -3, minus 2 becomes -7. So now I just add them together. 10 plus -3 is 7, and 10 plus -7 is 3, which is the same as before. And then again, we can shift by -3, and we'll see exactly the same thing. We can shift our data around, right? Shift our values and advantages around, and for different pairs of values and advantages, we end up getting the exact same Q values, which is a little bit of a problem, right? This will lead to unstable training because the neural network's goal is to predict what is the advantage of the different actions at the state and what is the value, the overall value of this state. But if different combinations of advantages and values give exactly the same Q values in the end, it's not unique. And so this is the non-identifiability issue. The solution to this is mean centering. So all we're going to do is take our advantages, the advantages we computed, right? 2 minus 2, minus 3, minus 7, whatever it may be. We're going to average them up. We'll subtract them from the advantages and use that instead. How does mean centering fix it? Well, let's just look at one example. So in the original, right, we had 5 plus 2 minus 2. So the average of plus 2 and minus 2 is just 0. And so my new A prime, which is mean centered A, will be plus 2 minus 0, which is plus 2, and then minus 2 minus 0, which is minus 2. And so we're just left with the same 7 and 3 from before because nothing happened. But now, let's say we shifted everything over by 5. So I have 10 minus 3 minus 7. No problem. What's the average of minus 3 and minus 7? Well, that's minus 10 divided by 2, which is minus 5. And now let's just check. If I do 10, or if I do minus 3 minus -5, that's minus 3 plus 5, that's 2. And if I do minus 7 minus -5, that's minus 7 plus 5, that's -2. And so my new Q values is going to be the value 10 plus my 2, right? My mean centered. So 10 plus 2 is 12. And then 10 plus -2 is 8. So we can see, even though we shifted it by the same constant, because we mean centered our advantages, right? Because we mean centered all of our advantages, we now get different Q values or unique Q values for these different value advantage pairs. And that's super important. This is how we essentially introduce identifiability. There's actually a couple ways you can do this. Mean pooling is the most common, or just, averaging is the most common. So that's what we're going to be doing. And basically the reason this works out is because mean centering just adds a constraint. Right? If we mean center our data, then the sum of all that data must just end up being 0, right? And we can see that right here, right? We can see that 2 and -2 is 0, 2 and -2 is 0, 2 and negative, it's always 0, right? So basically they always end up being 0. And this introduces the identifiability, right? Now we have unique values for different pairs. And so very simple, all we do now is we go ahead, compute our advantages from our neural net, just like we had before, but now we just go ahead and take the average of these advantages and then subtract that average from everything, essentially doing that mean centering operation. And then just like before, we add the values to that and we now have our Q values. And this just ensures that we get unique Q values for unique pairings of advantages and values. Okay. And so what changed from before, if we go back to our very first figure, right, the main place we started, what we wanted was in our setup here, right, in double DQ, we decoupled action selection evaluation. We had some neural net that predicted the Q values. We had some target neural net that was just a lagging copy that predicted the target Q values for the next state. And then we just did this indexing operation, right, to actually compute our TD values. And then we use that TD value to actually do our mean squared error, right, mean squared error. Well, all that changed is the model, right? Instead of our model directly predicting Q values, our model's now going to be predicting the advantage and the values. And then from there, we can compute the Q values. And it'll look like this, right? So we'll have exactly the same setup. We'll have a Q model. Q target will be exactly the same Q model, just a lagged copy, and nothing else changes, right? Exactly the same way. And that's basically it, right? So nothing too crazy. So we can go ahead and implement this, which will be also very, very simple. We can do class Dueling DQN nn.module def init self input state features, which is going to be 8 for the lunar lander that we're working on, and actions. There's only 4 actions you can take in lunar lander, and then hidden features is going to be 128. So we can do super dot init, and then just like always, we're gonna have 2 linear layers. So it's going to be nn dot. I mean, you can have as many as you want. I'm just going to do 2 input state features to hidden features, and then self dot fc2 will be another linear layer that's going to go from hidden features to hidden features. And now here's the key idea. We're going to have a self.value function. The value function is going to be nn.linear. It's going to go from hidden features down to 1 because it's one number that represents the entire state. So for whatever input state we have, we're going to have one number that represents the value of that state. And that's it. And then we'll have self.advantage. Again, another linear layer that's going to go from hidden features, but now it's going to go to num actions because the advantage linear layer, this projection, is supposed to learn what is the advantage of the different actions I can take at this specific state. And now that we have both of those things, we can just set up our forward method. So forward self x, and it's going to take x. It's going to be, let's just use relu as our activation, self.fc1 x, and then x is going to be f.relu, self.fc2 x. And we can now compute our value. So value will be self.value x. This will tell me for, again, every single sample, every single state, what is the value, overall value of that specific state. Then we have our advantage function, which is supposed to learn self.advantage x. What is the advantage of the different actions I can take at that specific state? And what we can now do is compute our mean. So advantage mean is going to be just advantage.mean dim equals -1, because it's going to be, again, remember, this is going to be on a batch size by hidden, or by num actions, right? All the actions I can take. So I want to take the average along the num actions dimension, so the last dimension. And we'll do keep dims equals true, right? So we don't lose that dimension, so we can broadcast. And so then our advantage is just going to be the advantage minus the advantage mean. That is mean centering our data. And so our final Q values is going to be the value plus the advantage, just like we saw. And we can return Q. And that's it, right? That was basically the setup, right? All we did is we take our, pass in our state, we compute some advantages, we mean center them, and then we add the values to them, and that produces our Q value. And that's it. So we can now go ahead and just make sure it works. It should be fine. There we go. Yeah, so it's already training. This doesn't take very long. It's not all that interesting. The main takeaway here was just that. So we can actually go ahead and just stop training because I already trained it. We can just look at the video, right? So here you go, right? You train it, nothing too crazy. It's just lunar lander, right? So it's a very simple environment for us to mess with. The main goal, though, is, again, the entire purpose of this is to add a little bit of stability to training. So I'll just show the Dueling deep Q, And you can see we'll have slightly smoother training curves, right? Nothing too crazy, right? So there you go. But that's it, right? So this was our last kind of minor extension on the DQN algorithm. So you've seen DQN, double DQN, dueling DQN, and this advantage method, this advantage function, is going to show up over and over and over again in almost all the methods we'll be looking at in the future. So I will see y'all in the next one.